Okay, now we know AP is equal to BP. We know that simply because by definition they have to have an equal distance from the distance from A to a point needs to be equal to B to a point. So the distance from A to the point P should be equal from B to the point P. So AP equals BP. Hence, if AP equals BP, these two things are equal. That is to say, this Z minus Z1 here must be equal to Z minus Z2 there, because these two are equal. Thus, we can conclude that this is the equation that contains all the information to represent a perpendicular bisector, given that you have 2 points, one point depicted by Z1 and the other point depicted by Z2. I've said finally let us finish with loci involving a stated arc or angle. That's what I'm going to do after this. But before I do that, actually, I did want to add a couple of some information. Note that Z1 and Z2 will be given to represent A and B. So for example, here's Z1 and Z2. And also note that the Cartesian form of this line, this is simply a linear equation here, can be obtained by substituting x plus iy for z in both situations. So I can put x plus iy in here and x plus iy in here, they're the same. And utilizing the absolute value or the length can be calculated by way of Pythagoras' theorem or Pythagoras-esque relationships. Then you will be able to find the linear equation that represents that line. Okay, so finally let us look at loci that involves angles or arcs. And this is what we're going to do. We're going to take a look at this circumstance here. Okay, so the argument, also known as theta, can be given, whatever is in here can be described as what that argument is. And what I'm going to do is I'm going to take this z minus z1, which we're comfortable with, hopefully, because I introduced it, given something that's quite perhaps an interesting concept, a circle. Z minus z1, again, relates to this z, this minus z1 down here, z up there. And as you can see, minus z1, z, and that's what z minus z1 represents. Hence, it should not be too strange that I've gone z minus z1 represents from down here to here. And so what does that mean? What does that matter? Why does that matter? Because it represents AP. You travel down z1, travel up z, you get AP. What is arc? Arc is the angle from normally from the real axis or the plane. But in these circumstances, because Z1 has raised up the original position, it's actually just parallel to the plane. So what I can do is I can say that you start at 180, this is meant to be parallel to the plane. So that is to say that these two lines should be absolutely parallel. And so what's happened is I consider this line, I've moved minus Z1, I've gone Z, and this line here, also known as a half line, is an angle from that parallel line to the x-axis or the real axis here. This angle is what theta is. And so arc z minus z1 is this angle in here, theta. Say, for example, in these circumstances, we can say maybe it's 80 degrees. So it'd be arc z minus z1 equals 80 degrees. Z1, most importantly, before we move on, what's Z1? Z1 will state the point of A. The point of A. Z will state the vector-esque position. So imagine this is more as a line. Let's pick a different color. Imagine this as a line that could touch anywhere along the half line. So it could be something like this, and it can continue up like so, as long as the angle is still theta, and that you still have to move down Z1, and Z1 is stated clearly as a point, and the angle starts at a position horizontal to this plane, which is equivalent to the real axis in the complex plane. Be aware that the angle is measured and measured from, and recall where the angle is measured from, it is measured from the straight line, and recall that pi is 180 degrees. It is stated consistently in radians. So here I've illustrated the idea that you can have Z could be touching across any point on this half line. And I've stated very, very clearly that's what we mean by half line. Some examples will come later, but please be aware before we do some examples, we're going to go from minus pi 2 pi is always where theta will be described as, so be aware of that. That is established as part of the definition of arg. It's not universal. It is normally the case, but it can be changed in some circumstances, some different fields of mathematics, engineering, and physics, so on. And so let's tackle, therefore, 2 problems. I've got 2 problems here. And before that, I just want to give you an example as to how Z1 could manifest. If Z1 were minus 1i, for example, imagine Z1 were in this position here. If Z1 were minus 1 plus I, then in that situation, you would again, I would say, well, create a line horizontal to the plane. The angle is horizontal from that point all the way up to the line for which Z will be describing itself, right? So let's say, for example, in this circumstances, the angle was 120 degrees. Then you know Z is minus 1i. You produce a line horizontal to the real axes. You map out 120 degrees. Therefore, the half line must be this here, and Z could be anywhere along that half line. Here's another one. Let's assume that Z1 is minus 1i. So Z1 in these circumstances is there. Now, again, first thing I do is I decide to create a horizontal line that is parallel to the real axes. There it is. Not the best level of parallel, but remember, this is not to scale. I then map out an angle. Let's say that this angle again is 120, 140 degrees, whatever I wish for it to be. I create that angle. In these circumstances, it would be negative. Lovely negative angle will be given. Please be aware of that. Remember, it's minus pi, 2 pi, and negative angles can definitely be given. Then I state the half line that matches that angle and position. Okay, given those 2 examples, let's do these questions. So question 1, I'm going to indicate on a single Argand diagram the set of points for which arg z minus 4 plus 5i is equal to pi. So again, there's the angle, there's where Z1 manifests itself. And in the second one, we're going to do Z plus 6 equals 1/4 pi to conclude.